Hello, y'all. Welcome to lesson 138 of my DB chemistry curriculum. Today, I'm covering structure 3.2.8. This is an HL topic. In this topic, we're going to be talking about mass spectrometry or mass spec of organic compounds, which can cause fragmentation of molecules. With that, we'll deduce information about the structural features of a compound from specific mass spec fragmentation patterns. So we'll include references to the molecular ion, and we'll look at data within the data booklet. This will mostly all be from section 22 of your data booklet, as long as that doesn't change again. So we've talked about mass spec, and when we've talked about it, we've used it to determine molecular formulas. But in organic chem, what we can also do is we can determine structural features of organic compounds. And that's what we're going to be looking at today, as I said in the intro. So how do we actually do that? Well, let's take a little bit of a look at what a mass spectrometer actually is. So I'm going to draw it out, but you can find images online. I don't suggest you drawing it out yourself unless you really want to. So it all starts with this nice curved vacuum tube. Oh, and I'm trying to get my iPad to recognize a curve, which it did before. And you know what? We're just gonna do this kind of manually. So we have this nice curved tube, and this is a vacuum chamber, and a couple things happen. So first, we have to put vaporized sample in the top. So whatever you're looking at, you have to vaporize it into its gaseous form, and then you bombard it with ionization, with electrons until those electrons strip off another electron from that compound. Once you do that, you then accelerate it. So you force that compound to move through this tube, which has a very big electromagnet. And finally, it's got a little detection thing at the end. And what happens is, based on the mass of the sample, that sample will either deflect more or less than another sample. So if we look at its pathway, whoop, it'll curve around, and based on the mass, it may deflect more if it's lighter or less if it's heavier. And so from that detection, we can actually figure out what the mass of that sample is. That goes into a little amplifier, which increases our ability to detect it. Amplifier. And then it gets recorded and charted. So that's the basic principle around mass spectrometry. Now, I'll just highlight some of those initial points. Gaseous compounds are ionized to form, and this is very specific, positive molecular ions. And we refer to it as capital M plus. Uh, Sometimes we'll refer to it like this, M plus. And that dot, very much like a dot in free radicals, represents a single unpaired electron. Unpaired electron. When we represent this as a formula, ionization can be represented as such. A gaseous molecule gets bombarded with an electron, which then strips away another electron, creating a cation of that gas. And 2 electrons. So we end up with this molecular ion. This is what we refer to as a molecular ion. If we did it with something like ethanoic acid, we might see CH3COOH plus an electron reacts to form CH3COOH plus 2 electrons. Now, you might have noticed something really important here, which is the formula stays the same. And because of that, so does the mass, because as we know, electrons have negligible mass. But you may have also noticed that it's now positive. And as we learned, these molecules don't want to be positive. They don't want to have that lost electron. That makes them quite unstable. So they become unstable. And due to that, they will actually break into fragments. 2 fragments. My handwriting got a little terrible right there. Specifically, we have our positive fragment, also referred to as the cation fragment, and our neutral fragment. Now, mass spec only sees positive ions. It does not see neutral things, so we'll never detect a neutral fragment. But we can detect these positive fragments as well as the positive molecular ion if it remains stable enough to hit our detector. So when we look at this, what we're going to be seeing a lot in our mass spec is our positive one, our positive molecular ion, our positive fragment, and we do not detect our neutral fragment. So we can detect cations. This small m represents the fragments of the big M. So we can only detect the cations. Furthermore, fragmentation occurs in many places. And we'll see that in a second. But if we think of ethanoic acid, I'm going to draw it out here. We can actually have fragmentation occur right between the carbons. We can have fragmentation occur between the hydroxide. So we can get different fragments of different sizes that will show up as different things. Because it occurs in many places, and because mass spec only only detects positive fragments, this will create a fragmentation pattern. So this is a lot of words you've had yet, so let's actually look at what a fragmentation pattern looks like. So pulling from my images, we can see a fragmentation pattern. Oh, it didn't load. There we go. We can see a fragmentation pattern of ethanoic acid. Let me just lock this so I don't screw it up. You'll notice a couple key features. There are, first off, a lot of different peaks. So I pulled this one from Cognity, but we can identify some aspects of these peaks. Right here is our molecular ion. The molecular ion is always going to be the furthest right, having the most mass because it has not broken up. So right here, you'll see it at 60. We'll have an n+1 peak, but we'll discuss that in a later video. But we see our big peak right here. That represents an unbroken version of our cation of our original compound. Then we have all these different peaks. We have a peak here at 43, a peak at 45, a peak at 29, a peak at 15. So we have to determine kind of what's going on here in this compound. Um, we can even see this peak right here at 31 maybe, who knows. So we'll go ahead and discuss some of these, but we have to always start from our molecular ion. So now, how do we actually gather any information from this? Well, we actually have to add the thing from the data booklet, which is going to be this table right here. We can use this table to look at the mass loss from our molecular ion to determine any neutral fragment that has occurred here. You'll notice that, for example, a 29 peak has a couple different options, so it's kind of sometimes difficult to figure out which one it is. But we'll practice this a little bit. So if we're looking at maybe, we'll do the one that says try this yourself. So our original mass is 60. So we're going to use a little formula here. The mass of molecular ion minus the mass, minus the mass, and actually I messed this whole thing up. The mass of our molecular ion, M plus, minus the mass of our positive fragment should give us the mass of neutral fragment. So if we're looking at our peak at 45, our original mass is 60, minus our mass of our positive fragment, which is 45, gives us 15. Therefore, our neutral fragment here is probably CH3. So we can tell that at 45, which represents this nice big one right here, we have, oh, sorry, that's 43. At 45, we have CH3 remaining. So if our fragment loss is CH3 and we know that we're dealing with ethanoic acid, that means our positive is probably this. So CH3 is that, and I'll use my colors. Therefore, our positive fragment is probably COOH positive. And together those make our ethanoic acid. So it's kind of like figuring out a puzzle from only getting half the pieces and determining the other half. A little bit of terminology that I'm going to add in is this thing called base ion peak. Base ion peak is literally just going to be our most abundant positive fragment. So if we look up here, our most abundant positive fragment is our cation fragment of CH3CO plus. So we've lost OH. You'll notice here at 17, so we're looking for the peak at 17, which would be that one representing the other portion of it, being the lowest because base highest peak is the other one. So what this basically means is we can analyze fragments to determine unknown compounds. And so the best way to do this is just by practicing. Mass spec is definitely something that I think you just have to practice a lot to kind of get it all figured out. So I've got an image right here that I've also gotten from Cognity. And so we're going to use this to practice a little. So we have this empirical formula, C2H6O. We're going to use this mass spec right here to determine many things about it, as well as the table that we have up here. So let's just go through question by question, which will kind of help us organize our thoughts. The relative molecular mass of the compound. It's going to be the furthest peak to the right. That is 46. Therefore, MR of the compound is going to be 46. Then we can look at the mass of the base ion peak. That's right next to it at 45. So our most abundant positive fragment has a mass of 45. Then the formula for the molecular ion. Well, we know the molecular ion is just a positive version of the molecule. And so first we have to look at our molecule. We know the empirical formula is C2H6O. So if I do the math, 12 times 2 plus 6, or plus 1 times 6 plus 16 gives me a mass of 46. Well, turns out my molecular formula and my empirical formula are the same formula. Therefore, and I know that because my empirical formula has the same mass as the molecular mass of my compound. Therefore, this is just going to be C2H6O with a positive. That's all you have to do for the molecular ion, add a positive. Now the actual harder parts, which is we're going to find the neutral fragments for 15 and 31. So I'm going to go ahead and use the formula I had before. M plus, mz of m plus minus mz of little m plus equals the mass of my neutral fragment. So the mass loss here is going to be 46 minus 15, which equals 31. So that's going to be the mass of my neutral fragment for the peak at 15, meaning this peak. Therefore, my neutral fragment is going to be likely OCH3. So that's going to be OCH3 at MZ15. That is the neutral fragment. Now at 31, it's just the inverse. 46 minus 31 equals 15. And I know from my previous one, 15 represents CH3. So my two neutral fragments are OCH3 and CH3. Honestly, while we've already completed the question that's been asked, we can likely determine what this compound is from these neutral fragments. If it breaks off as CH3 and OCH3, we're likely looking at an ether of C, O, C, instead of an alcohol. I know that because if I was looking at an alcohol, we might get a fragment of OH, which has a mass loss of 17, and that doesn't appear here. We don't really have anything often at the 17 mark. So from this, I know that the compound we've been given is an ether, and we just use mass spec to determine not only the fragments lost, but what our compound actually is. This is the power of mass spec, and it's something that you should try and practice quite often. I hope this helped, and have a great day.